Alright, in this video we'll be going through the 2017 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. Thomas's car has an interior light that turns on when the door is opened. When the door closes, there is a time delay before the light turns off. The time delay is determined by the time constant of the resistor-capacitor circuit, which is an RC circuit. Describe what is meant by the term time constant. So the time constant is the amount of time taken for the current or voltage value to change by 63% compared to its previous value, okay? So you can write that in. The diagram below shows an RC circuit. The capacitor is initially uncharged. After the switch is closed, the battery supplies 7.2 times 10 to the negative 4 joules of energy. Calculate the energy stored in the capacitor when it's fully charged. Alright, so there are two methods you can use to solve this problem. The first one we can do is by using EP is equal to half QV, okay? And we also know that Q is equal to CV, and so if we plug this into here, we get EP is equal to half CV squared. We're given the voltage of the power supply, and as we know, when the capacitor is fully charged, the voltage across the capacitor is going to be equal to the voltage across the power supply. And so therefore our EP is going to be half times our capacitance value, which is 5 times 10 to the negative 6, multiplied by 12 squared, and this equals 3.6 times 10 to the negative 4 joules. The second method in which you can solve this problem is by taking 7.2 times 10 to the negative 4 and dividing that value by 2. If you don't know how that comes about, I go through it in my capacitance videos on my electricity playlist, so you can go check that out. And you can see how the capacitor only stores half the energy that is supplied by the power supply, okay? So another way you can do that is get 7.2 times 10 to the negative 4 divided by 2, and that indeed does equal to 3.6 times 10 to the negative 4 joules. Explain why this energy stored in the capacitor is less than the energy stored by the battery. Alright, so this is exactly what I just explained in the previous part. Only half the energy that is supplied by the power supply is stored within the capacitor, and the rest of the energy is lost due to resistance, and therefore it escapes as heat, okay? And again, I go through this more in my capacitance videos on my electricity playlist, so you can go check that out. Draw a graph of the circuit current against time for 15 seconds after the switch is closed. Data points should include the initial current and the current after one time constant. Alright, so firstly, we need to calculate our time constant. We know that our time constant for an RC circuit is equal to the resistance times the capacitance. Our resistance value is 8 times 10 to the 5, and our capacitance value was 5 times 10 to the negative 6, okay? And this gives a time constant of 4 seconds, okay? Now we just need to find out our max current, and so to find that, I max is obviously equal to the voltage divided by the resistance in the circuit. The voltage is 12 volts divided by the resistance, which is 8 times 10 to the 5, and so this gives a current value of 1.5 times 10 to the negative 5 amps, alright? And as you can see, this current axis is in terms of times 10 to the negative 5, and so therefore our max current value is going to be over here, okay? Now we know after one time constant, which is 4 seconds, so 4 seconds is right here, this value is going to drop by 63%, so it's going to be 37% of the original value, okay? And so we can take 1.5 times 10 to the negative 5 multiplied by 0.37, and this gives 0.555 times 10 to the negative 5, alright? Amps. And so therefore, we are going to be roughly right here, okay? So that's after one time constant. And now we can find after another time constant. There are two ways of doing this. We can either take 0.555 times 10 to the negative 5 and times it by 0.37 again, or we can take 1.5 times 10 to the negative 5 and multiply it by 0.37 squared, okay? So either or would do the trick, and this equals to 0.20535 times 10 to the negative 5 amps. And so after another time constant, which is 8 seconds, which is going to be over here, okay, we are at 0.2, which is going to be roughly over here, okay, and then we can do after another time constant if we want. So this is after 12 seconds, and this will be 16 right here, okay? And so those two values are going to be 1.5 times 10 to the negative 5 multiplied by 0.37 cubed, and 1.5 times 10 to the negative 5 multiplied by 0.37 to the 4, okay? So those two values are going to be 0.076 times 10 to the negative 5 amps and 0.028 times 10 to the negative 5 amps, okay? And so we're going to be roughly over here and then roughly over here. And as we can see, we have a nice exponential decay, like so. There we go. Explain why the graph has the shape you have drawn. Alright, so obviously the graph has a decay curve, okay, so it's an exponential decay. Alright, so the reason why it has this shape, which again is roughly like this, okay, where this axis is current and this axis is time, so this is current over time, okay. Alright, so when the power supply is initially turned on, we have a max current, and so therefore charge begins to flow at a maximum rate. And so therefore charge will begin to accumulate onto the capacitor plates. As more charge begins to accumulate onto the capacitor plates, okay, as more charge begins to accumulate, the charge that is already on the capacitor plates will begin to repel any oncoming charge. Okay, this is because like charges repel. And so therefore, the charge is going to slow down, meaning the current is going to decrease. Okay, and that's what we see. It starts to decrease right here. Okay, however, this still means that charge is still being put onto the capacitor plates. Okay, it's just going at a slower rate. So eventually, the capacitor will be fully charged. And at this point, the voltage across the capacitor is going to be equal or almost equal to the voltage of our power supply. And in this case, we have two almost equal opposing EMFs, and so our current approaches 0. And so you can write that in words. The time constant of an RC circuit can be changed by adding a second capacitor as shown below. Explain how this affects the time taken for the capacitor to charge up. Alright, so when we add capacitors in parallel, the equation is like so. And so therefore when we add a capacitor in parallel, like we have over here, our total capacitance will increase. Okay, and because our time constant is equal to the resistance of the circuit multiplied by the capacitance of the circuit, as the capacitance has increased, therefore our time constant will increase also. And so therefore the time taken for the capacitor to charge up or become fully charged is increased, okay? And you can explain that in words. Alright, so this is an absolute monstrosity amount of words, so I'm not going to read that out loud, you can read it yourself. So essentially, we have a situation where we have an RL circuit, okay, and it wants us to state the voltage across the ideal inductor once the current has reached a maximum value, okay? So once the current has reached a maximum value, which we can see over here, this is when the current is flowing at a steady state, okay? So the current is no longer going to be changing. And so at this point, we know this is when the inductor acts like an ideal wire. And we know that the voltage across an ideal wire is equal to 0, right? Because voltage is a potential difference, remember? And so the potential difference between 2 points of an ideal wire is 0 because the amount of energy per coulomb of charge at one point of an ideal wire is equal to the amount of energy per coulomb of charge on another point on an ideal wire, okay? And so therefore the potential difference is 0. And so if the inductor acts like an ideal wire when the current is at a maximum state, therefore the voltage across the inductor is equal to 0 volts. Alright, explain why the current does not immediately reach a maximum value as soon as the switch is closed. Alright, so I'm going to put in the EMF equation for our inductor, like so. So before the switch is closed, the current is at 0. Okay, so when we close the switch, current is going to obviously start to flow. And so therefore, there's going to be a high rate of change of current, okay? And so therefore, there's going to be a high EMF being induced by this inductor. And remember, due to Lenz's law, this EMF is going to oppose the change that caused it. And so this is going to be a back EMF. And so therefore, this EMF is going to oppose the oncoming current, meaning this prevents the current from rising to a maximum value straight away. Now, after a while, there is no longer going to be a rate of change of current. And so therefore, this back EMF is going to die down, allowing the current to eventually reach a max value. And so you can write that in. Immediately after the switch is closed, the back EMF across the ideal inductor is 12 volts. Using the dotted line on the graph on page 6, calculate the self-inductance of the ideal inductor. Alright, so we know that our equation is equal to negative L, change in current all over change in time. Okay, and so if we use this graph, this seems kind of odd why we would use the dotted line instead of this line, okay? The reason for this is because as we see, we have current here and time here, okay? And so the gradient of this graph is going to be our change in current all over our change in time, okay? Because this is our rise and this is our run, right? So rise over run. And so what this dotted line actually shows is it shows the gradient at this section right here, okay? And so as we can see, we have the voltage value when the switch is initially closed, okay? And so that is when the voltage value is going to be at a max. And so we also need to find out the gradient or the rate of change of current when the switch is initially closed, which is going to be this point right here, okay? Finding out the gradient at this point is kind of hard, it's kind of small. So what they've done, they've helped us, and they've just extended that line all the way up, okay? And so we get a current value of 6 and a time value of 0.1. And obviously, the gradient of this entire line is equal to the gradient of this line right here, okay? Same value. And so therefore, our rate of change of current is equal to 6 all over 0.1, and so that's equal to 60 amps per second, all right? And so we have a EMF of 12, and we're trying to find our inductance, okay? We don't really care about the negative in this case because that's just Lenz's law, but we're just trying to find the value itself, so we don't really need to care about that negative. And so that's multiplied by 60, and so therefore 12 divided by 60 is equal to our L, and therefore this gives an inductance of 0.2 henries. There we go. Sparks require very high voltage to be produced. Explain how this is possible for a spark to be produced across the gap in the spark plug when the switch is opened. Alright, so we have our diagram here. When this switch is opened, okay, so it was initially closed and then we opened it, alright, this causes the current within this primary coil to drop to 0 very, very quickly. And so therefore our rate of change of current is very, very, very high, okay? And so therefore, due to this equation right here, our EMF produced by our inductor is also going to be very, very high, alright? And so that causes a very rapid change in flux inside the primary coil, okay? And so this change in flux is transferred into the secondary coil, and so therefore that change in flux induces a very high EMF in the secondary coil due to this equation right here, alright? And because of the ratio of the turns, okay, as we can see here, the primary coil has 50 turns and the secondary coil has 80 turns, okay? And so therefore, because of this equation, NP all over NS is equal to VP all over VS. If we want to find the voltage in the secondary, we get VP all over NP divided by NS. And because this value is 50 and this value is 8,000, this bottom number is going to be very, very small, okay? And so therefore, the voltage in the secondary is going to be very, very large, all right? And so the voltage in the secondary is great enough to jump the gap of this gap right here, thus producing a spark, okay? And so you can write that in. Also, this gap results in an almost infinite resistance, okay? And so obviously our time constant is equal to L over R. And so if this R value is very large, then our time constant is very, very small. And as we know, the EMF induced by our inductor is related to the time constant. And so therefore the EMF is also going to be very large. And so you can write that in. It is important that the wood used in buildings does not have much water in it. Thomas uses a parallel plate capacitor with a wood as a dielectric to measure the water content in the wood. Water has a higher dielectric constant than wood. One way of measuring the water content in wood is by using the circuit shown below. Thomas connects the circuit and makes the following measurements. Calculate the peak voltage of the AC power supply. Alright, as we know, VRMS is equal to V peak divided by square root 2. Again, if you don't know where this equation comes from, I go through it in my electricity playlist, so you can go check that out. However, you do not need to know where this equation comes from for NCEA. Alright, you can just plug and play if you will. So we can rearrange for VRMS times square root 2 is equal to V peak. And so therefore we're given our RMS voltage as 12. And so therefore 12 times square root 2 is equal to 16.97 volts. Calculate the RMS current in the circuit. Alright, so we know that VRMS is equal to IRMS multiplied by our total impedance. Okay. In this case, we can see that the reactance of the capacitor is 23.5 ohms and the resistance of the resistor is 50 ohms. Okay, so our total impedance is equal to square root 50 squared plus 23.5 squared, okay? And so therefore this gives a total impedance of 55.25 ohms, okay? And so therefore IRMS is equal to VRMS all over our total impedance. And so therefore our VRMS is 12 divided by 55.25. And so this gives a current value of 0.217 amps. There we go. Explain what would happen to the circuit current when the wood in the capacitor is replaced by a similar piece of wood that contains more water. As it says over here, water has a higher dielectric constant than wood. And so therefore, as the equation for our capacitance is equal to the permittivity of free space multiplied by our dielectric constant times the area all over the distance. Assuming all three of these values remain constant and just our dielectric constant increases, therefore our capacitance will increase, okay? And so because our reactance of our capacitor is equal to 1 all over omega multiplied by our capacitance, if our capacitance increases, therefore the reactance of our capacitor will decrease. And so therefore, as our total impedance is equal to square root xc squared plus r squared. If our reactance of our capacitor decreases, then the total impedance of our circuit will decrease, and as V is equal to IZ, if our total impedance decreases and our voltage remains the same, therefore our current will increase. And so you can write that in words. An inductor is added in series with the capacitor and resistor in the circuit. The reactance of the inductor is 35.7 ohms at 151 Hz. The reactance of the capacitor is 23.5 ohms at 151 Hz. Thomas adjusts the frequency until the current is maximum. Calculate the resonant frequency. Alright, so when the circuit is at resonance, this is when our reactance of our inductor is equal to the reactance of our capacitor. We know that the reactance of our inductor is equal to omega L, and the reactance of our capacitor is equal to omega C. And so therefore we can say that omega squared LC is equal to 1, okay? I just multiplied both sides by omega c. And so we also know that omega is equal to 2 pi f, and so that means omega squared is equal to 4 pi squared f squared, okay? So 4 pi squared f squared LC is equal to 1. And so now we can rearrange for f squared, and we get f squared is equal to 1 all over 4 pi squared LC. And so therefore f is equal to square root 1 all over 4 pi squared LC. And so now simplifying this, we get f is equal to 1 all over 2 pi square root LC. So this is the equation that we need to find our frequency. We obviously know what 2 pi is because that's just a number. But what we don't know is the capacitance and our inductance, so we need to figure that out. However, we are given the reactance of our inductor and the frequency, and the reactance of our capacitor and the frequency. And so because we know that XL is equal to omega L and XC is equal to 1 all over omega C, therefore our capacitance is equal to 1 all over omega times XC, and our inductance is equal to XL all over omega. And so therefore plugging in our numbers, for our inductor we get 35.7 all over omega, which is 2 pi f, which is 151 Hertz. And for our capacitance, it is 1 all over 2 pi f, again 151 Hertz, multiplied by our reactance, which is 23.5 ohms. This gives a value of 0.037 henries, and this is 4.49 times 10 to the negative 5 farads. Alright? So now we can just simply plug in those numbers into here, and we get our frequency is equal to 1 all over 2 pi multiplied by square root 0.037 multiplied by 4.49 times 10 to the negative 5. And this gives a frequency of 122 Hertz. There we go. Explain why the current is maximum at the resonant frequency. So as stated before, when we're at our resonant frequency, this is when the reactance of the inductor is equal to the reactance of the capacitor. As we know, the reactance of the capacitor and the reactance of the inductor are 180 degrees out of phase. And so if they're equal to each other and they're 180 degrees out of phase with each other, they're going to cancel each other out, alright? And so therefore, if we look at our phasor diagram, okay, normally the reactance of our inductor will come up here, and the reactance of our capacitor will come over here, and our resistance will come over here, okay? And therefore, depending on if the reactance of the inductor or the reactance of the capacitor is larger, the total impedance will either come this way or it will come this way, okay? But if the reactance of the inductor and the reactance of the capacitor are equal to each other, that means they, again, like I said, they will perfectly cancel each other out. And so what we're left with is just the resistance of the resistor. And so our total impedance is equal to our resistor. Another way you can look at this is we know that our total impedance is equal to square root XL minus XC squared plus R squared, okay? And so if these two values are equal to each other, obviously this will equal to 0, and so we get our total impedance is equal to square root R squared, and so our total impedance is equal to R, alright? Same result. And so because of this, obviously now the reactance of the inductor and the capacitor are not taken into account in our total impedance. Obviously this means that our total impedance is at a minimum value. Okay, and because of V is equal to IZ, alright, if our total impedance is at a minimum value and our voltage does not change, this means that our current must be at a maximum value. And so you can write that in. And with that, we're done. See ya.